So in this particular problem, we have an enclosed area of 3,000 square feet. So we don't know the dimensions, so I'm going to label those X by Y. And we have shrubs that are going to be lining up 3 of the sides. So I'll denote that on the diagram. And then finally, we have one side that is a fence. So I'll go ahead and label those other sides with our variables here. So we've got shrubs costing $25 per foot. So 25 times y plus y plus x, so x plus 2y, plus fencing, which is $10 per foot, times the amount of feet, which we have x feet. So that's the total cost. And if we're going to find the minimum total cost, we need to take the derivative of our cost function and set it equal to 0. So the first piece is, let's go ahead and eliminate one of our 2 variables by setting up the fact that the area is equal to 3,000. So therefore, y is equal to 3,000 divided by x. In this case, it didn't matter which of the 2 variables we isolated. Probably pretty much the same level of difficulty. So now I'm going to go ahead and make a substitution into my cost equation and do a little bit of simplification by distributing the 25 to both of those items within the parentheses. Which results in the cost function being 25x plus 150,000 over x plus 10x, which is 35x's plus 150k over x. So in other words, times x to the negative 1. So our first derivative would be 35 plus 150,000 times negative 1x to the negative 2. We're going to set that equal to 0. I'm going to multiply through by x squared in order to get it out of the denominator. So that gives us 35x squared minus 150,000 is equal to 0. And then by isolating x squared here, we calculate that x is equal to the square root of 150,000 over 35, which is approximately 65.465 feet. And the reason why we can get rid of the negative amount is because it doesn't make sense in the context of our problem. Therefore, by plugging this value back into our equation above, we get 3,000 over 65.465, which gives us a y dimension of a value 45.826. Now we need to be able to verify whether we have a max or a min for our critical point. First, let me write down the total cost then, based on this set of dimensions. would be about 45.82 and 58 cents, so somewhere around that. Now let's go ahead and test. How do we know that this is the minimum cost as opposed to the maximum cost? Now we don't have to worry about testing our endpoints because our endpoints aren't included in this problem because it wouldn't make sense contextually. So I'm going to use the second derivative, and I will plug in my x value at the critical point into my second derivative. So first I'm going to get my second derivative here, and plug in 65.45 or 65 into that. And that will give me a value that is 300,000 divided by x cubed. And so plug in 65.465 into there. And we don't actually need to know what that value is. We just need to know that that quantity is positive. And because of the fact that the second derivative is positive, this tells us that our original cost function is concave up. Hence, it will allow us to know that we have a minimum instead of a maximum value, as you can see from this diagram here. If you've got a concave up function, your critical point is going to end up being